So my name is Eric Esmarek. I work at Intel in our software division. Yes, Intel does have a software division. Usually, people always think of us as hardware, company, but there's a few thousand people in doing software. My team, sorry. Come back. My team's charter is really enabling Java for various new Intel technologies. And I'm specifying technologies because in the past it was mostly around the core. New CPUs will come out, new instructions come out, and it will enable Java, the JIT mostly for new ISA. In the past few years, we have kind of evolved, and we are looking at anything that Intel does, from memory to FPGAs to new storage, and the list goes on, accelerators as well. And we usually push all of our changes into OpenJDK and Oracle, and we have a pretty close relationship with the Oracle Java team. At the same time, to kind of showcase some of the works we do, we also participate in many of the open source projects from Apache and others, just to show how those new technology can work. So some of the things we work with is Apache Cassandra, Spark, Hadoop, HDFS, HBase, the list goes on. And we really try to modify the code, enable the new things we are, and push upstream it to Apache. Make sense? I don't, not my side. I don't just want to talk to you guys, have it the whole, I would love to be more interactive. So if you have any questions or any comments, anything else, please raise your hand. I'll be happy to repeat them out loud. I have a lot of slides, but they are really, there's a big part of the slides here, the core idea that I want you to walk away with. Kind of what are we doing with persistent memory, and how to think about it. And then there are some other slides with code samples and details that if we have time, we get to them. If not, they will be published and you can take a look at this. There's also a few GitHub projects out there that have links to you can look. And you can always email me later on if you have any questions or comments and such. So time-wise, we should be okay. All right, so legal stuff. Now, so what's really memory computing? I won't go over, its value and various approaches because there's plenty of other talks around here that don't mention this. It is really, at the end of the day, trying to get one single thing, get away from doing any I/O, right? We want to eliminate going to the disks, and that's what this memory computing stands for, where we no longer have to stream data from the disk, and we can just do it in memory through the random access. That's really what it boils down the whole thing here, right? So why don't we do it anymore I/O? That's the main question that you should ask yourself. It's a pretty easy answer. It's slow. I mean, end of the day, as compared to our CPU and memory technologies, is relatively, slow. It's performance. I mean, access and things are measured in microseconds versus nanoseconds and such. So, and this is the list of things that kind of gets in the way, right? From no longer, your CPUs cannot access the data right away. It has to go through a whole bunch of interfaces. And that's why we try to get away from I/O, right? But, disks will not go away, or at least not yet. We still need the capacity. We need to make that durable. We need the low cost. And with the fact that today, from cars to cell phones to watches to everything, you always collect data, you will need this capacity and durability characteristics so you can analyze it. Eb said earlier on that he thinks everything with memory, it might be, but just the amount of data is being created makes it kind of difficult today at least to store memory. So if we take a kind of a look, high-level look, 1,000 feet, comparing storage to memory, it's kind of obvious that they complete each other, right? Capacity-wise, we need the terabytes versus gigabytes. Memory, again, is not durable. You can make it through some software, replication, and others, but end of the day, if you shut down your whole cluster, you will lose your data if it's in memory. You need the disks. Access, this is where memory has a clear advantage, that you can access your data, random next to your data. No need to stream the data from your disk, transform into some kind of data structures, and then analyze them. You access them immediately, right? And then bandwidth, even our fastest drives today, I think, go up to 3 gigabytes per second, whereas memory, depending on your DIMM configuration, it can reach 60 gigabytes per second. And then latency, same characteristics, right? Disk is measuring microseconds, whereas memory is nanoseconds, right? So as of today, at least, we still need both because we need all of those properties to make our application run properly, right? What if someone gave you hardware that can do the best of both worlds? You know, has large capacity, has durability, allows you for random access, has fast speed of access, you know, both latency and bandwidth. Sounds pretty interesting, right? Who would say no to this kind of technology? So can we do it with just pure disk stock? You know, can we have a new SSD which is ultra fast and can do much higher reads and so on? Well, we've done some work at Intel, and we measured the performance of just different storage. And what this graph shows you here, ignore the workload really. What matters is the blue portion is your access to the media, right? This is where you read the data. The colorful, you know, different greens and yellows and pinks are essentially all the overhead. This is what you need to do to get through your controller, to get through various file system caches, to get through, you know, a whole bunch of other things. So even if we were to shrink the media, make our new SSD, which is 1,000,000 times faster, you still not going to get away from the everything else overhead, right? So that's where we kind of don't believe that, you know, having a pure SSD will give us the performance you're looking for, especially in this conference like this, you know, memory access. Questions? Make sense? So this is what I just said, you know, your performance is not only based on your NVMe media. There's a whole bunch of other things around there. So this is where, you know, Intel and some others have built this technology. And it does provide most of the properties I listed earlier on. And it is this persistent memory. It looks like a memory DIMM. It's plugged into your machine, and you can do persistence. It will have a high capacity, not other things. I brought a sample here, just to give you an idea that I'm not making stuff up. I can pass it around, but this is how this looks like. Normal memory DIMM, right? It will have some of the properties I talked about before there. And I will talk more about this. Questions? Okay. So, kind of what's persistent memory, right? It's memory-like performance. It's not a DRAM replacement. It's really today, on a single machine, you have both DRAM and this new media type, this new memory. This time it's byte addressable, right? You no longer need to, in Java specifically, serialize and initialize your data. You can access your data directly on that memory and read your Java objects, other things. It's durable. That means you can shut down your JVM, or you can shut down your application or your machine and come back, and you have access to data immediately. No need to read it into anything. Right? It will have larger capacity, and as I said before, you will bypass at this point all of the kernel and all of the hardware overhead from the previous slides. Questions? Comments? Okay. So the graph from before, same graph, same workload. I don't know if you can even see it on here. I wish I had a pointer, but on the very right, it's essentially the same access to that data, right? And the slides will be online, so you don't need to take copies, pictures if you want. We not only shrank the media access, but we also have completely removed all of the hardware, you know, that's in between there. And that's, you can see the difference in performance on, you know, on this graph. There is a, and there's some SNIA people in here too. So now, how do we program this memory? It's a brand new concept. This is something that never existed. You have this memory that high capacity, durable, and a bunch of other things. How do we even write code for this? So a whole bunch of companies got together, Intel is one of them, and put together a programming model on how we should be accessing memory. And I'm not going to go in details what they do, and I think there'll be other talks around this, but essentially they come up with a set of ways to access and manage the memory and such, right? And on top of this, Intel and some others build a library called NVML to facilitate someone to access that memory and use it in their C++ code, right? So the obvious question is, if it's just memory, why do I need these libraries, right? I don't have anything specific to write to memory. I use a malloc and I have data. And, well, it's more complicated than this here. There's a few things you can kind of imagine. One, what happens today when you have a memory leak in your application? What do you do to solve it? Easiest way. Shut down your application, come back, and it's gone, right? You have a memory leak in persistent memory. What do you do? Shut down, come back, it's still there. So this library will help you with some of those things. It will help you allocating data. We'll make sure that there are no, if there are memory leaks, you're able still to free that memory and such. So it's really a pool of helper functions. It also deals with transactions. So this is another interesting topic, which I won't spend too much time on, but think about it this way. Today, when you do a write into your application, you say integer I equal to 5, right? That's not going to be pushed right away to memory. It will reside in the CPU caches, right? Same thing for here. So if you set something in memory, it will be only in the cache at first. And eventually, through cycles and such, it will be pushed all the way to memory. If your machine were to die before that's done, you think that this was committed and the value is set, but it might not be, right? So again, what do you do? Well, you need to essentially flush your cache, your CPU caches. And who really wants to do this as a Java developer or even C developer? This is something to be built in. So this library allows you, just by using some of the APIs, to have transactions. When you say, I want this value to be equal to 5 as a transaction, once this returns to you, it will be committed and it has been made durable and it's there, right? I don't know if some of you can imagine why that's important. That's actually extremely important. Any ideas? So one example I have is a linked list. Imagine you have a linked list in that memory, and you want to insert something, and you just basically change the pointers, before and after on everything. But somehow, those setting the pointers still resides in your caches, in your CPU caches. Your machine goes down. What happens next? You most likely will lose your linked list. There's nowhere to access to it anymore, right? Not a good scenario. That's something that will not happen on a disk, because on a disk you rewrite bytes, you can always get back to it. So here, we need to deal with this. So you can write your own code today without using LVML. I mean, there's no need even to do this, but you will have to deal with all of those issues, and that can become pretty complicated. So there's a whole bunch of people that have been developing this for quite a while now, and it's open source, and you can take it and start writing your C code. Any comments or questions from anyone? So now, what about Java? Why do you even care about Java? There are a few reasons. First, it is still the most popular programming language in the data center. I think last time I looked, 40% of all applications in data centers run Java, and that's true. If you look on Apache, there's about 500 projects, and I think 300 of them are based on Java. Second most popular language is C++, which are like 50 projects only. I know it's not the measure of the world, but it gives an idea that most of the new things is still being in Java. And one of the main properties of Java, main characteristic, is that it's really meant to abstract the hardware from the developer. You shouldn't know what's underneath you. You just kind of use APIs, right? Sure, you can do all the things you want through various hooks, and people have been doing it for years. I mean, anyone who wrote Java code found Java limitation either on GC or on new hardware or something, and they use JNI and Safe or a whole bunch of other things. I mean, that's a well-known way to do things. But as a result, it's often not portable. Whatever you wrote for one machine, one platform might not be moved really well to another platform, either from OS perspective, on hardware, and so on, right? often there is an overhead associated by going to GNI, and maybe not safe, but GNI or other things too, right? And finally, Oracle can at any point choose to stop supporting something, right? And I think unsafe is a good example where this slowly removing support for unsafe going forward in next year. So that's where I think we come to the conclusion there's a need to have a more standard, more kind of generic Java access to that new memory without the developer having to do any special tricks. Any? Okay. Raise your hands if you have a question. So we really we don't think there's just one single approach. There are multiple ways to do what we want to do. And for that reason, we kind of spent, our time for the past almost 5 years now thinking how someone writing Java code or writing Java middleware, and we're really talking here about server-side, data center-side software, right, can be using Java to use this persistent memory, this new huge media. And I will talk about all three ways that we kind of come up with. So the very first one is where your entire Java heap will be allocated in a new space. That means no code changes. All you do, you have a new parameter, this -xx heap directory, and that's it. At that point, your Java heap will reside on persistent memory. Pretty easy, right? So why would you want to do this, right? Well, there are plenty of instances that we run with some customers when they run literally hundreds of JVM on a single machine. And many JVMs are not active. They're just really there, waiting for a signal of some kind to do some task and then go away. So today, even though that data is being paged in and out from the drive, there are two things. It still uses a fair amount of DRAM, but at the same time, if you want to page it back, it's a pretty slow process because you're doing I/O at this point, right? So by doing this, you're basically going to say, hey, those applications are not really active most of the time, but I still want them to have memory-like performance, and I have tons of memory. Let me just allocate my Java heap on this new memory type. So this is part of Java right now. There's a JEP around this. It should be out sometime next year. I don't know if you know, but Oracle has changed their Java releases from 3 years cadence to every 6 months cadence. So we're hoping this will be made sometime next year, right? That's the very first usage. The easiest of them all, in the sense that no code changes required. You will note this is not meant for performance reasons. This is really meant for additional functionality that kind of helps you with some of your problems that people have expressed they had with the Java applications. Any questions or comments? So now, the second way is it's slightly more involved from the perspective of the developer. It's where you can specify which part of your code will be allocating objects on this new memory. And the way this works essentially is that you know for a fact that you want to have some large data structure. You want to have a hash map or something which is really large, and I want to keep the whole thing in memory at any given time. So what we do is this: we give you yet another new flag which says, hey, this is the amount of memory I want to allocate in persistent memory. And from this point on, anytime when I use this keyword, this new API here, I can't read on this screen, sorry. Heap set allocation target, anything between the start and stop essentially will be allocating memory in this new space on the persistent side of things. And the way we do it underneath, those of you who know about garbage collection and G1 collector mostly, we just create a new G1 region in persistent memory. So everything behaves and looks exactly the same as before, except this one region lives in persistent space, right? So here, it's really the developer with very little of minimal code changes. You add those two lines saying start allocation in this new media, do your work, and stop allocations. Everything in between will be allocated in there. If you have a question, I can tell. Do you have a question? No. Okay. Make sense? So we have done some work on this, and this to experiment with Apache Spark. I don't know how many of you know Apache Spark. Who knows Apache Spark here? Oh, a chunk of you. Where when you have RDDs, and at sometimes you want to keep them in memory, for example, for later computation and so on, today, they're going to be based on your memory sizes, potentially spilled to disk and then serialized and deserialized again if you want to read them. What we said is saying, hey, all of the RDDs are going to live in this memory. And it gave us a pretty great boost in performance in some of the workloads around there, just because you no longer have to go to the disk any time, right? All data is always, all your RDDs are always in memory at any given time. It does create an additional pressure on GC, but because you cannot control when you're going to put there, you can assume that the data will be long-lived and not something that you need to GC regularly. And you can make that space relatively large as well, so the G1 collector will not go over it as frequently. Okay? So that's, again, another usages. So, go ahead.
Question, how large of memory did you basically allocate? Did you test it with large amount of memory, gigabyte, terabyte?
We have, yeah, we have.
How high did you go up?
So I don't remember the exact sizes, but it was more than 256 gigabyte. I know, we haven't, if you email me offline, I can get exact data. The idea was, to keep your normal heap, I think 64 gigabyte, and then we had this additional region, which was, I think 256 or more gigabyte. Really just to, and I think it does involve some knowledge from the developer side where you need to know, you really want to put their things that are long-lived, they'll be using over and over again. So the hash map is a good example. You have hash map when you put stuff constantly in, right? Thank you. I'm glad you asked that question because this is my next slide. Everything I talked about right now was not persistent, and it should be kind of obvious, right? I mean, if you look at this here, we're talking about the heap being in that space, and then talking about the chunk of G1 to be there. This is a case where we're using this memory as volatile. I know it's kind of doesn't make sense, but this is where this memory allows you to be either persistent or volatile. So volatile means, you shut down your JVM, it goes away. It is no longer there. So it's not. You cannot retrieve that data. And that's when the next part we'll talk about true persistence. So even though we call it persistent memory, it can be used either as volatile memory or as persistent memory. And we found a need for both. Many cloud applications and others don't care about persistence because they might not come back and see the same node next time around. They just want this big memory, right? Does it make sense? So there's no persistence angle at this point yet. It's just really additional new memory. And I just put you the links of some of the Java work we have done. It's checked it in there. So now, I'm glad you caught this. This is what I'm talking about here right now. So everything we've done right now for the first, for a while was around volatile usage of this and not persistent. We were struggling to figure out even how to use persistent. What's the usage model? Why would you want to have a persistent memory for your Java application? And only after spending quite a bit of time with some of the NoSQLs and some other databases that we figured this is probably the best usages, where your data from Cassandra to HBase and some other ones, your caches or your data should be there after a reboot. This is what Abbe talked before, right? You no longer need to, you don't need to repopulate your caches. You don't need to repopulate your stuff. It's going to be there right away. So for that, we said, okay, how do we use this in Java? How do we expose this to Java developers, right? And once again, there's no one single solution. We have 3 different solutions. And one of them is to provide a collection of Java classes, or I should say, it's a library of Java collections which expose persistence. And I'm going to show you some of the collections. Other ways, like, can a user build its own persistent classes? So if you have a object, some type employee or anything else, and you want to make persistence, how do you build that? And finally, some of the groups we talk to and companies, including GridGain, they're like, well, we don't really care about any of those things. We really want a low-level API, which allows me to deal with my own Java byte buffers, my own unsafe space, and do whatever I want there. I don't care about going through your software stack. So we build that as well, okay? And I'll talk about this. So, I don't know if you can read this, it's pretty small. This is the first set of Java persistent collection that we have. What that means, all of them are essentially looking exactly like their Java util or whatever classes, except their persistence. And that means when you instantiate them, when you put objects inside, the class will be there. And this, I'll give you an example of this works. And this is where, answer your question, you shut down your JVM, they'll be able to come back and get back your collections. This list is growing. We picked, we are picking what we believe as we go along what we need for build some of the software. With the ultimate goal to have a pretty full coverage of this. And again, the goal will be to have the entire thing in OpenJDK at some point. And we're working with Oracle on that too. So, some kind of details on this. So, on that, in persistence, what we store is really just the data itself. There's no code, right? It's really just a Java object layout in there. They behave exactly as Java objects. There's almost no difference. The main difference is we don't GC this. We use some, on a short version, a reference counting method. So once there's no more references to it, we delete it. And that's exactly the kind of fight the whole, how big we can go, right? And I would say this is a little bit in the experimental phase. We don't know the final solution there. But the reference counting seems to work relatively well. Again, same sizes as I said before, about 256 gigabytes. And this is where, remember I talked before about transactions and how do we do this in C++ by using that library. Here, we basically have APIs that when you do a put into one of those collections, when you insert something, their APIs will come back and that guarantee you durability. Underneath, we do everything that when they, it essentially has ACID properties. You will do a put into a hash map. If and when this returns, you know data was put into persistent memory. If the machine were to die during your put, we have a rollback feature in there that essentially you will just leave as just before you made the call, right? So nothing will be lost or corrupted. So the example I gave you before of the linked list will not happen, right? And that's probably one of the most complex part of the whole thing here. Questions? That's a very good question. So this is on the to-do list for us. Security and version changes are kind of on the to-do list. But I think we're going to just deal it with some kind of stamp on the objects on the version. And absolutely. So as I said, and this is one of the places where I would love more feedback. We haven't done that yet. We haven't implemented this, but we have a list. I wish I brought the list of things that we still don't necessarily know or understand. And that's why all of this is in open source. It's a GitHub project, and we are, as I said, been working across the Apache community, been working across many companies out there who wants to use it today, getting their feedback. It's important, it's just not top priority. We have other issues to solve first. But yeah, it's a very good question.
Does the data survive the termination of the application and restart? And if so, how does the restart instance the application?
I will show you code. I have code for that. So, okay. So this is a really tiny code snippet to answer your question. So the first line, you basically create your new persistent integer array, right? And then what you need to do is you need to add your object. We have essentially, if you think of it, a object directory per application, right? And you set your data to be, to 123 value 0, shut down your JVM, you shut down machine, and that's how you get back to it. It's the big difference compared to a file. It looks like a file almost, right, at this point. The big difference, all we do is just point to it. We no longer have to read any data back to DRAM. Everything just resides over there, and it's there immediately, right? That's kind of the difference. That make sense? And we presented this more complete, I think, at Java 1, and there's more examples and stuff. But if you go to GitHub, there's tons of examples we put in there. Any other questions? So that's how you can create any of those classes, any of those collections, and essentially get them back later on. Go ahead. So this is not a heap anymore. This is us managing that memory, right? We are no longer using G1 heap or anything else, right? Oh. So what happens when the heap in persistent memory getting corrupted? So how is that different of a file problem? If a file gets corrupted or something goes bad, it's exactly the same. I don't see a major difference. No, we don't, but the access is kind of the same, right? So the way, think about it this way, I'm creating my data structures, right? Let's stick with this example, in the integer array. We're gonna lay it out in this persistent heap using some APIs which make sure that we guarantee transaction and such, right? Everything is ever there, right? At that point, if something goes corrupt, I don't think that are you looking like for a checksum or something like this, kind of like you do on your files? Tell me, so yeah, I haven't even contemplated this scenario, right? So how would you get a 1 byte corrupted? The difference is here you cannot access that memory directly yourself. You cannot write to it. There's no pointers. There's no way to access it on your own. You're doing it through our API, right? So it's kind of a control access. Does it make sense? So a file, I can open a file, I can write to it, I can do things to it anywhere I want, right? Here it's really, the only way to get corrupted is if our API has some issues, or if the system somehow corrupts the memory. And that's actually an interesting question. I don't know the answer to that one. And I don't know if you guys happen to know what happens if the memory gets corrupted. The operating system? Yeah. It's a good question. It's actually a good comment. I haven't, we can only control so much on our side, right, on the application level. So we do have, as I said, this whole rollback in the case where the machine or the application dies as you insert things. So we have that mechanism built in. We take snapshots before and after inserting something to avoid this in the process of inserting and modifying the collections. But we don't have really anything when this is being corrupted outside of my application. Something else does it. So that's a good point. Yet another thing to think about. I saw a hand somewhere there too.
You did mention asset guarantees.
Yeah.
So how do you guys handle compound operation? Is it some application level graph transactions, or do you have an API to?
So this is where we are relying on VML for that at this point. Most of the asset transaction things, we took the C++ code and kind of wrapped it around in this first version. So we didn't write this in Java right now. So I forgot to kind of preface this. This first version of this, we're really looking at functionality. We're really trying to identify how can I use this, and then once we have that, and we don't. Clearly, people come up with plenty of holes. Once we have that, then the idea is to provide that functionality within the JVM itself. Any C code that today is being used through GenI, whatever, would be part of the Java itself. But yes, it will be there. So I'm not a database asset guy to explain you all those things, so I won't have all those answers. But I know who will if you need more. How much time? 15 more minutes. So, as I said, so you remember, the first 2 or 3 examples were using the volatile mode, kind of, where your heap, no code changes. Second, it's kind of, you need to think now, what do you want to use and how and where you want to restore it, right? This becomes more involved. And now we have another mode where you can essentially just derive from existing classes and create your own persistent objects. And I have 2 examples. One easy one, setting one which I won't even go into it, and I'm not the one who wrote the code, and it's kind of complex, but this is the easy one, right? You just want a persistent tuple to, and you just derive from it, build your class around it, and you can just use it. That's straightforward, right? There is another way, and this is the one I won't go over, but this is your Java class, and I can't see on the screen, it's too small. You have your Java class, typical Java class employee here, and we have code on how to transform this into a persistent class. So, the key thing is now you have to extend no longer from object, your traditional Java thing, but from persistent object. That's the first step. And then you're gonna basically just have getters and setters, and you need a few other things in there, like the string field under one that I don't even want to talk about here. So it's there, right? It's there. We are not really spending too much time on this right now because this is where you need to worry about some of the stuff you do on your own. And again, I think when people start developing code to this, they will have more to add to it. Our main focus is really, I would say, on this in first place. And then, this is where we found the most interest, initially at least. You can control, you can allocate your space. We provide low-level APIs, we call them, which is kind of, ironic in Java, where you can allocate your own persistent byte buffer or persistent memory locations and then do your own thing. So anyone who has code which deals with byte buffers or deals with unsafe of the Java heap and so on, this is the most applicable thing today. You can take this and you can start manipulating them. You need to deal with your own persistence, consistency, and all the stuff. But this is where we have spent some time working across and 2 other big applications. And Apache Ignite is one of them, where most of the data seems to be living on the Java heap, and that allows you to kind of almost completely map this to the API. Again, we're looking for more feedback on this as well. If you see the example here on this include flush, you need to be flushing your own data caches, not data caches, CPU cache and such. You need to be doing everything on your own. Does that make sense? So I have the feeling that people will be using either this when you deal with unsafe or just be using this. And for example, we have modified Cassandra, Apache Cassandra, to stop. I don't know how many of you know any of the NoSQLs well. Data is always moved between like 3 or 4 layers of caches, right? So Cassandra has like 4 caches and constantly migrates from place to place, making it that performance for what's in cache is really good, but if you go to disk, clearly it's maybe a big difference. And most of the customers today are looking for this 99th percentile SLA. That's the main goal. We modify Cassandra. We are modifying Cassandra right now so that all of the storage is done in persistent memory, and you only have to go to one place to get your values and put your values. No need to go anymore to your 3 or 4 caches, look through your filters and so on, and find the right SST table and so on. So that's where we kind of are using as prototype to experiment with those things. Go ahead.
So is that Cassandra version available to try?
It will be available. So we haven't released it yet into GitHub. We are working with the Apache community right now to have it upstream all the way. But this year, before the end ends, we'll put it in GitHub just for people to play around with. And sometime in 2018, we are working with some partners to upstream it all the way to the Apache source code. Right? Everything is dependent on the fact that we need full Java support for this. And right now, it's kind of two pieces, just because we have to gather this whole ecosystem to work with us. This is another question, same as the corruption thing. So the way, I didn't talk much about it. I should have maybe, but end of the day, the way the CD works underneath is that you mmap a file onto persistent memory initially. And then the big difference is, as compared to a traditional mmap, data is never brought into DRAM. It's always in place, right? So now your security or your kind of user permission and so on is the same as a file. You can specify groups, policies, and all those things on a given file. But this is yet another topic where I would call advanced topic at this point, because we have so many other unknowns and kind of things that we want to deal with, that security is on the list of things to spend more time on. Right? And Oracle, we had this just recently talk about this, and we are aware this story is kind of weak there. And I would love input on this again, right? Okay, so I talk about the LoRaWAN API. Any other questions on this? Also, I said this, as I said, we use this in Cassandra. We use this on some other smaller workloads. And we spent some time on Apache Ignite and a few other things with lower level API as well. The cool thing about here, which I mentioned, is those of you that are not that familiar with Java, OpenJDK, they don't have branches per se. They have like future projects, like Panama and a bunch of other ones. So OpenJDK Panama, it's available today from OpenJDK website, we're using their APIs for this. We're really using their infrastructure. That means very little code changes for the user, and you can try that almost today. So, any other questions on this? So now, applications of this memory. To be honest, I think sooner or later, we all going to be using this. It's kind of like your cell phone today, right? You don't even think about storage underneath. It's just memory. Everything is there. So I think that this is where all of the application here in memory will be using rather sooner than later, right? But it's not that easy end of the day. There's still plenty of things that we need to kind of work on. And I think the biggest problem is this whole idea of such a new technology. It's hard to distinguish what do you want to persist, what you don't want to persist. I feel like there are obvious things, like Ebe mentioned caches. It's the easy thing. Let's persist caches within memory and so on. But I think there's a lot more. You can do a lot more smarter things there. And as we build those prototypes and the software, we learn there's more and more and more we can do, right? It really feels to me like the early days of the iPhone, or when the first iPhone, there was no apps, and then someone built this app for level something, and people are like, this is so cool, I can level. And then they start building smaller apps, and now to the point where they have advanced anything there, right? We are almost at the same point here. This will take a while to kind of build up. So we're trying to, as Intel, we're kind of trying to, creating the building blocks to it and enabling some of the well-known software, but it's really for everybody in this room here to start thinking, how can I build a machine where my memory is always there and it's large, and I don't need to serialize data or deserialize data, I just access it. And I think this is not going to be a one day or a month change. This is a completely different way of thinking. And until you start actually thinking about it, it's much more harder than it sounds. Some of the initial things, people always think, oh, large memory, that's cool. Let me just use that as storage. That works too, but I don't think this will be eventually the final way of using this. And we are learning more and more, as I said, as we build this stuff. The software will need to be fully re-architected. Right now, most of us are adapting existing software. that was written years ago without this in mind, right? I think going forward, software will be written for that. So, go ahead.
So you said it's extremely fast, I believe that, but how fast is it compared to DRAM? So what is there any performance? It should be some performance penalty.
There is some performance penalty. The performance is essentially between your DRAM and your fastest SSD, right? I don't know the exact numbers right now. It's, as I said, it's in nanoseconds accesses. It's not in microseconds. The throughput is much bigger than what your SSDs will give you and so on. So I'm a software guy at this point, and I think I will need to check what Intel's latest official releases were there. Do you know what? Yeah.
I'm going to talk about it a little bit tomorrow morning, but not with specific numbers.
Yeah. So think of it as slightly slower memory, really. So that's why you need to say, as I said, as you build your application, you don't want to have everything there. The most critical items which are memory sensitive, you want to keep in DRAM. It's stuff that you know, and often in Java, let's be honest, there's some places where the software layer above it is really your problem and not necessarily the access of the data itself. So we have seen this in Cassandra and other places. I don't know about your applications, but the one I have looked at, yeah.
Think of it as much closer to DRAM than it is to storage. And one way to think of this is, you know, what does the CPU do when it has a cache miss and needs to go to memory? The application stops, you wait for the memory to come in, and then it resumes. As opposed to storage, you get swapped out, something else happens, you know, much later it comes in. This is much more memory. So think in terms of memory. Is it exactly the same as DRAM? No. But exactly the same behavior happens at the system.
Right, I just want to have kind of like the 2, 10 times, right, order of magnitude.
If you use NVDIMMs today, it's exactly the same as memory. So NVDIMMs are one way of doing it. It is memory. There's other new media coming. It depends on the media. But it's going to be close enough to memory so that when it's way too fast in order to get swapped out and then come back in. So the CPU loads the cache and then you keep going. It's much closer to memory than it is to storage.
And one thing to add, all of this software is not just for Intel side of things. This will work with whoever else builds personal memory. So you will get different answer from Samsung, Intel, or Micron, or whoever else does it. Right. So we are not limiting ourselves just to Intel. I'm enabling the ecosystem for here.
How do you address
Scaling?
scaling?
In what sense?
Distributed scaling.
So, there's no different than today. You know, if you run Cassandra, Spark, and all those guys, which scale out, essentially, right? Talking about scale out, every application allocates its own. Oh, you mean in the case where some nodes have it, some don't have it? That's a good question. This is something which is, today when I'm talking to some of the larger customers, they would often have uniform nodes for a cluster. So if they have 20 nodes cluster, I'm making this up for a company there, they will all more or less be identical. They will not have different core count, different accelerators, different things per node. Right? If you have your Cassandra cluster, they'll be all uniform. Otherwise, the work is unevenly distributed, which leads to kind of uneven results, right? You will not have the same throughput or the same latency based on which machine you went to, right? So we are basically, this is application level scaling.
Why do you say nothing about the operating system update? So let's imagine I put the box. So how do I get access to the persistent memory with the known data?
It,
I know you cannot allocate memory chunk in the exact place.
for this to work, latest kernel has what they call ext4 DAX. It's a special file system for this memory. So the kernel is dealt through this ext DAX part, where I should show you earlier on there. But basically, before you can even use this memory, you will install this file system on that device. So that's how it's being dealt through across reboots and such.
Make sense? Okay.
Different storage tiers that you talked about, right? So those storage tiers, the way data is going to be stored, some persistent data is going to be managed in the storage tiers, are all going to be API agnostic. So your APIs which you're going to expose is going to take care of the storage tiers.
That's right. That's what SNIA does, essentially, right? The whole SNIA programming model was not built for Intel. It was really built across for all persistent API, media, not just from Intel. I'm being kicked out right now, so being waved like crazy from both sides. If you want to have other questions, you can grab me after this. So.